Hi everyone, still here talking about quantum mechanics, quantum electrodynamics, all that cool stuff. One thing that I want to emphasize in this video is that the quantum superposition that we talked about in the last video, which I was making the argument is really a consequence of a complete acceptance of this idea of indistinguishability. That superposition is really at the root of everything that's weird about quantum mechanics. It's the superposition that fundamentally produces the wave-like interference that we talked about initially. This wave nature is really a consequence of this superposition that, the motion of an electron is really a combination of all its possible kinds of motion that are compatible with the initial measurement. One really strange example is called quantum entanglement. And so in kind of a simplified way, imagine you have two particles that are bound together, okay? And suppose they are moving at they're stable, they're stuck together. And imagine they explode. They fly apart, okay? Now, if I take one particle, it's far away on the left-hand side here, and I grab it, and I measure its momentum. Fine, I can do that. Now I look at the other particle that's over here. They started with an initial momentum of 0, right? They're at rest. So conservation momentum tells me what that guy's momentum is. Now suppose I go and I measure where it is. Haven't I just violated Heisenberg's uncertainty principle? I've measured the position and I've calculated the momentum. That violation is actually impossible. So there's something wrong with the way I set up this experiment and described it. And it's because of the fact these two particles are actually entangled with one another. Their fundamental wave fields are still connected even though they're separated in space. So when I measure the momentum of the particle on the left, it affects the momentum on the right in a random way that I cannot predict. And so even though I'm able to measure the position, I cannot infer that that measurement is clean. And that is the root of this quantum entanglement. And this also goes by the name of the EPR paradox. It's one of the ways that Einstein sought to basically show that there was something weird going on in quantum mechanics, something that was fundamentally incorrect, basically by producing this kind of a contradiction that there's no way particles separated by an arbitrary distance are still communicating with one another. Now, there are a lot of technical difficulties that I'm completely skipping over, but that's the root of what we mean by things that are entangled quantum mechanically. Now, there's this person named Bell who discovered this fundamental inequality that basically would rule out, it puts an upper limit on the amount of information that can be extracted from systems like this. And the thing is that even though the particles are entangled, they're not entangled enough to actually transmit a signal from one to the other. So we can't actually use them to communicate. Although I will admit there are a lot of unknowns going on here. So there's a very strong active research area in terms of understanding this quantum entanglement. And a lot of interesting results have been shown to occur that this entanglement, it violates the principles of special relativity, moves faster than the speed of light. However, like I said, we can't utilize that, and nonetheless, there's this very strange angle to this quantum superposition that is that's fascinating.